Now let's move on to another approximation method in quantum mechanics, again suitable for time-independent problems. As we have already seen the perturbation theory and variational method, this is the third approximation method that we'll have to discuss in this category of approximation methods for time-independent problems. This method is widely known as WKB Approximation to commemorate the three physicists who introduced the method in quantum mechanics and are Wenzel, Kramers and Brillouin. It is known under different name in different regions. In Britain it is known as Jeffrey Wenzel Kramers Brillouin Approximation, JWKB. In Holland it is called KBW method, and in Hungary it is called BKW method, etc. Though these names are related to the founders of the method or the physicists who coined this method, there are some other astonishing names under which also the method is well known. We will come across these very shortly as we move advance with the WKB approximation. General introduction to WKB. The method, as I have already told you, is introduced by Wenzel, Kramers and Brillouin. This method is further referred to as the semi-classical approximation, though as per the demand of our syllabus we discuss it as the third approximation method. This we might have discussed as the first approximation method. This actually give a connection between quantum mechanics and classical mechanics in terms of the classical action and quantum mechanical action. Classical action, I'll represent it say as 0 and quantum mechanical action as say yes. Why it is called semi-classical approximation and why it is called phase integral method, all these things will be discussed very shortly. And at this point I'll tell you one thing: this method is suitable for generally one-dimensional problems, as in the case of one-dimensional harmonic oscillator, like that. Or of course you can apply this method to three-dimensional problems or two-dimensional problems as well. However, there are methods of decomposing them into one-dimensional problems. So in general, the method is suitable for one-dimensional problems or problems that can be decomposed into two or more one-dimensional problems. Now let's see the principle of this method. Following this, we will talk about the criteria for the validity of the approximation method also, and this discussion will evidently tell you why it is called semi-classical approximation, or how it is related to semi-classical approximation, or how it is one step ahead of the classical approximation. As you know, the classical equation for Hamiltonian is for a system that is moving with a kinetic energy subjected to a potential say V. Then the Hamiltonian is evidently the sum of the kinetic energy and potential energy, where kinetic energy is given in terms of the momentum as say p square by 2 mu plus V. And the corresponding equation of motion in classical mechanics could be written in terms of the Hamilton-Jacobi equation and in terms of the canonical equations. As you know, the Hamilton-Jacobi equation is h equal to minus time derivative of classical action. I have only one choice for action right now. That is why I have taken this action as say S as usual, or as you have discussed in classical mechanics, or say using standard textbooks like Goldstein. So Hj equation is h equal to minus dou s by dou t. From this equation itself, clubbing with the Hamilton's canonical equation, say dp by dt or pj dot equal to minus dou s by dou q, you can write the momentum of the classical system as the gradient of the action. As you know, h is already equal to minus dou s by dou t, and the canonical equation tell you qj dot equal to minus dou s by dou p and pj dot or dp by dt equal to minus dou h by dou q, or this is equal to dou by dou q of h. H is already minus dou s by dou t. So minus dou s by dou t. Of course, there is one more minus here. These two minuses will be vanishing, and we obtain dp by dt equal to, or dou p by dou t equal to dou by dou q of dou s by dou t. As these differential operators are commuting, you can write this as dou by dou t of dou s by dou q. Dou s by dou q is nothing other than, say, grad s. So that dp by dt equal to d by dt of grad s. D by dt then vanishes. You have, say, on the left side dou p by dou t, dou p by dou t equal to, on the right side you have this dou by dou t taken out, dou by dou t of, what remains is dou s by dou q. That is the derivative of action with respect to the position coordinates or generalized position. That is nothing other than, say, grad s. So time derivative of momentum equal to time derivative of grad s indicate that p equal to grad s. So this is something that you have already come across in classical mechanics. So substitute for p equal to grad s. The analogous equation for the equation of motion in classical mechanics corresponding to this classical Hamiltonian is given by minus dou s by dou t equal to, substitute p equal to grad s, we obtain this as, say, grad s whole square divided by 2 mu plus v. So this is the classical equation of motion derivable from the classical Hamiltonian. And quantum mechanical Hamiltonian also has the exact format. You have Hamiltonian equal to the sum of the kinetic energy and potential energy. Then why cannot we try an equation of motion in quantum mechanics or starting from this equation for Hamiltonian? Yeah, we will try it right now. An analogous equation of motion in quantum mechanics is nothing other than the time-independent Schrödinger equation, that is given by IH cross dou psi by dou t equal to minus h bar square by 2 mu del square plus v operating over psi, where psi can be written as e raised to I by h cross s of r comma t, where s here is being represented as a mathematical function of position and time is the quantum mechanical action. We are interested in obtaining an analogous equation, analogous to this classical equation, in terms of, say, classical action in quantum mechanics, that is in terms of quantum mechanical action. How come I come across this quantum mechanical action? This is also that you have discussed in quantum dynamics. You have seen that the Schrödinger equation in quantum mechanics is analogous to, or is complementary with, the HJ formalism in classical mechanics, whereas the Heisenberg formalism is complementary with the canonical formalism in classical mechanics. This you can obtain directly from the time-dependent Schrödinger's equation, IH cross dou psi by dou t equal to h psi, or h equal to take psi to the left side and I in the numerator could be written as a minus I in the denominator. It's a very basic knowledge from complex analysis. Minus h cross by I, psi is written to the left side 1 by psi dou psi by dou t, or this is equal to minus dou by dou t of h cross by I natural log psi. H cross by I is constant, natural log psi has a derivative 1 by psi dou psi by dou t in terms of time. Now this is identical with the Hamilton-Jacobi equation that we have already written here, h equal to minus dou s by dou t. This is also exactly of the form h equal to minus dou by dou t of this quantity in this bracket should be then nothing other than, say, the quantum mechanical action. As it is dependent on psi, the wave function, which is a mathematical function of position and time, S also needed to be a mathematical function of position and time. So that we can write S equal to H cross by I natural log psi. So that natural log psi equal to I by H cross into S, or psi equal to exponential I by H cross into S. We mean substitute this value of psi in the Schrodinger's equation. For that we will have to evaluate, say, dou psi by dou t and del square psi. Dou psi by dou t is derivative, time derivative of this exponential function, that is exponential function itself, which is being written as a psi into derivative of this quantity. Derivative of I by H cross into S is I by H cross dou S by dou t. And del square psi is evidently divergence of grad psi. That is, divergence of grad psi is gradient of this one. Gradient of this one is derivative of e raised to term with respect to the position coordinate, that is exponent has a derivative exponent itself into derivative of this one. I by H cross is constant into gradient of S. Now psi is also dependent on position, grad S is also a vector depending upon position. So this divergence has to be taken for these two quantities, and I by H cross is constant. I by H cross is taken out. Del dot psi grad psi, that's of the form divergence of a vector grad S and a scalar psi. That is psi into del dot grad S, which is del square S, plus second function grad S into derivative of this psi with respect to position. That is nothing other than psi into I by H cross into grad S. Psi into I by H cross into grad S is the second function. So you open this bracket, I by H cross psi del square S, I by H cross into I by H cross, make it say minus psi by H cross square. Grad S dot grad S is nothing other than, say, grad S whole square. This is the dot product of a vector with itself, and that gives you the square of the magnitude of the vector. Now substitute these values of dou psi by dou t and del square psi in the Schrodinger's equation. We obtain the analogous equation of motion corresponding to this classical equation in terms of action in quantum mechanics. That is, IH cross dou psi by dou t equal to minus h bar square by 2 mu. Del square psi is written here, plus v psi. Dou psi by dou t, IH cross into dou psi by dou t is I by H cross dou S by dou t into psi. Minus h bar square by 2 mu is used to open this bracket. Del square S I by H cross into minus h bar square by 2 mu is a negative term that is written here, and the positive term will be, say, this one. H cross square vanishes, minus make it, say, plus, grad S whole square divided by 2 mu is there into psi. Grad S whole square by 2 mu plus v. Yeah, psi is taken as a common factor, and this term becomes 1 h cross vanishes, minus I h cross by 2 mu minus I h cross by 2 mu del square S into psi. Divide the equation by psi, and simplifying this term, I square minus 1 h cross vanishes. So this is minus dou S by dou t equal to grad S whole square by 2 mu plus v plus minus I in the numerator is plus I in the denominator. So this is h cross by I into grad square S divided by 2 mu. And this is the quantum mechanical analog of the classical equation that we have already come across. And this classical equation has only this much portion, whereas quantum mechanical equation has an additional portion, that is h cross by I del square S by 2 mu. Suppose this term is not there, you cannot make it, say, 0, or of course you cannot tell you that this term is not there. It's an assumption that suppose this term is negligibly smaller comparing with the term containing grad s whole square. So when this term is negligibly smaller comparing with the other term containing s, or say grad s whole square by 2 mu, then the quantum mechanical equation of motion is exactly identical with the classical equation of motion. Or the only difference that the whole thing quantum mechanics can account for is in terms of, say, this term, h cross by I del square s by 2 mu. So now the question is, can you neglect this term? Answer is, of course, not. Because this term containing h cross, as you know, is of the order of, say, 10 power minus 34, 1.38 into 10 power minus 34. It is, of course, negligibly smaller, but it is still finite. And you cannot neglect this term in the case of those systems whose del square s by 2 mu, or their contribution to this one is of the order of, say, h cross. That is particularly important in the case of atomic and subatomic systems, where we most often make use of quantum mechanics. And this concept is nothing new as well. We already know that the basic fundamental principles that demanded quantum mechanics are the uncertainty principle and the de Broglie's concept of matter wave. In both these fundamental principles, we have already seen this quantity h, or say h cross. It is, of course, the finiteness of this Planck's constant that make quantum mechanics a necessity. So we cannot omit it. However, in the limit, this term largely exceeding this one, h cross by I del square s by 2 mu, then this equation turn out to be, or tends to be, the classical equation of motion. Or in the limit, del s whole square by 2 mu much greater than h cross by I del square s by 2 mu, that is, 2 mu vanishes. Del s whole square is much greater than h cross del square s in terms of the magnitude. That means, again, grad s is already, we have seen that it is momentum. So grad s whole square is momentum square, much greater than h cross. Del dot grad s is del square s. So this is del dot p, as p equal to grad s. So once p square is much greater than h cross times the divergence of momentum, then quantum mechanics and classical mechanics predict one and the same thing. Or quantum mechanics, or equation of motion in quantum mechanics, turn out to be the classical equation of motion. However, this approximation, or say this criterion, will be valid in the case of macroscopic systems only. In the case of quantum mechanical systems, you cannot neglect this contribution h cross del dot p, so that this equation of motion will be valid as a different equation of motion, unlike what predicted by, or contradicting to what predicted by, classical mechanics, with this much part for the equation. So this equation will be valid. This necessitates the quantum mechanical action S to be written in terms of a sum series in h cross by I. And this series may be written as a, making use of this approximation, this may be written as quantum mechanical action S equal to S0, where S0 is nothing other than the classical action that include the 0th power of h cross, or that is the one and only term devoid of h cross, plus h cross by I S1, plus h cross by I whole square S2, plus etc. So the overall quantum mechanical action will be some series in terms of different powers of h cross by I. But generally we will be satisfied with the term up to the first power of h cross, so that we make an approximation for the quantum mechanical action as S equal to S0 plus h cross by I S1. So with this action, we have the quantum mechanical action just one step ahead of the classical action. It is exactly this is why the WKB approximation method is referred to as the semi-classical approximation. The classical approximation for action is S0 is equal to S0. That include constant term, not constant term, that include zeroth power of h cross, which is then a function of position and time only. And in the WKB approximation, we take the format of the quantum mechanical action as say S0 plus h cross by I S1. So this is also an approximation. There are higher order terms, of course, but you know that h cross itself is a very meager quantity. Then higher powers of h cross will be further smaller again and again. For the time being, h cross itself is of the order of 10 power minus 34. Then h cross square will be of the order of 10 power minus 68, whose contribution will be definitely negligible. So we will be contented with the format of the quantum mechanical action being, say, this one S0 plus h cross by I S1, and hence this approximation method is one step ahead of the classical approximation and hence is known as semi-classical approximation. Now we will see the criteria for the validity of the approximation. This we have already come across while discussing the principle of WKB method. We have seen that the WKB method is valid when this criterion is satisfied. Grad S whole square is much greater than h cross del square S. That is, grad S whole square much greater than h cross del square S. We have seen that momentum P equal to grad S. So we substitute grad S equal to P. Then P square is dot product of momentum vector with itself, which is nothing other than the square of the magnitude of momentum. That is much greater than h cross del square S. That is del dot grad S. Grad S is nothing other than, say, P. And we have already seen that WKB method is suitable for one-dimensional problems, or we have already mentioned that WKB method is suitable for one-dimensional problems. In one dimension, we take this along, say, as usual, x direction. Del dot P then has the meaning of dP by dx. Rate of change of momentum with respect to change in position. So we have a dynamical system that is moving along the x direction. As it is moving, it will have a change of momentum, because for moving the object, a constant force needed to be acted on it. A force is nothing other than the measure of rate of change of momentum with respect to time. As this move, then of course there will be a change in momentum. Let P be the momentum at an initial position, say x, and at a different position, say x prime. Let P prime is the momentum. Then delta P by delta x is P prime minus P by x prime minus x. This has the meaning for this term, say dP by dx. So P square much greater than h cross dP by dx. This is the criterion for WKB being applied. Or we take this term to the right side, so that I will be writing this greater than in terms of, say, less than, much less than. Already h cross is there, P square is taken to the right side, and I have put one P under h cross, and another P is written under dP by dx. So this criterion become h cross by P dP by dx by P much less than 1. As you know, h cross by P is nothing other than the d Broglie wavelength associated with this moving particle. So we mark it as a lambda. Lambda into dP by dx by P is much less than 1. Once this condition is valid, you can apply the WKB approximation. Now, what does this condition verbally tell you? Lambda is the de Broglie wavelength of the particle. P is the instantaneous momentum of the particle, and dP by dx is the rate of change of momentum with respect to position, or the rate of change of momentum as the object moves. Once this product is much less than 1, this means that once the object is moving, or once an object is performing a dynamics which is such that as it moves over a distance equal to the de Broglie wavelength associated with that particle, then the change in momentum upon covering this much distance over the instantaneous momentum should be negligibly smaller. Once this condition is satisfied, you can definitely apply WKB method. So WKB method is applicable to those one-dimensional systems in which the fractional change in momentum over the instantaneous momentum over 1 unit of de Broglie wavelength associated with that moving particle is much smaller. Once this condition is satisfied, WKB approximation method could be used. You can find an analogy for the criterion for validity of WKB with the criteria for geometrical optics. See, in geometrical optics, or you will be applying geometrical optics, of course, light will be following a wave motion, but in geometrical optics we will be representing this in terms of a ray. This approximation is valid if and only if the fractional change in the refractive index suffered by the light upon covering 1 unit wavelength is negligibly smaller. Once this condition is satisfied, that is, the fractional change in the index of refraction suffered by the moving light wave over 1 unit wavelength of light, then you can consider this wave motion of the light as an extremely thin pencil of light. And such an extremely thin pencil of light is usually referred to as a ray of light. So it is under this assumption we will be considering a wave motion as a ray. Yes, an exactly similar approximation is there for the validity of WKB approximation as well. The fractional change in momentum over 1 unit de Broglie wavelength associated with the particle must be negligibly smaller. Once this condition is satisfied, you can have the quantum mechanical action associated with the system as one step ahead of the classical action, and such an approximation method is referred to as the WKB approximation. Now in the next video, we will derive a general expression for the WKB wave function. Then we will make some conclusions about the systems to which WKB could be applied.